wasted our time and money and effort and
Did it work in the end? I think that it was working.
it was just all projection.
So it must be working now. Can you check? Can you check if it works and if I'm audible?
It's not working.
I know. How did you find the XP?
Yeah. But the green screen doesn't work. Like we see the green screen, and you are super small.
Right. I'm quite big. But do you hear me? The sound.
I believe that we are using a different microphone. We have to change the microphone.
Can you check the micros?
Just a minute.
And if that happens, then this whole thing gets off.
Just a minute.
Well, it shouldn't be. It should be minus. This is the position. Yeah.
But
No, that's not.
are we gonna have the screen? Yeah, I didn't forget. Yeah, that's
Think about it back here.
This one is not.
okay. Maybe we
The public now?
stop the streaming and start it over.
It's physically.
What do you mean?
Below that. No, it makes no
Fine, we
sense.
still have time. It's still
The same as here,
10:30.
you have to, like,
No worries.
the thing is completely down. You can't have, yeah. In the beginning, it doesn't matter, in the cloud, in the beginning, it can also be here, like, you need to do determination, but it can't be here, like, the, Joyson, it can't be here. And the minus
Not
is
working.
like, when it's here, it's minus, and you also, if you go here, like atom, but for the, bay you see that some of these things don't make sense anymore, because you can constantly deviate.
It's working, but
Constant value, although it should
need
vary
to
because
fine
the x
tune.
is minus. But it's like no default constantly to be zero. Be helps.
Yeah, when the x is zero, then VA is
Constantly, if the x is smaller than zero, constantly defaults to be helps. Yeah. But it doesn't make sense because it's actually zero. So the problem is this x is like also in some other parts still used.
can you stand? This is the first time you are using OVS, right?
No. Second.
You can run.
Okay.
Yeah, are you going to teach from scratch or
And in this one,
uh,
like show,
like,
even like if
are you
x is
going to
bigger
do a
than
continuation of
this
something
x
on this
also-
topic?
No, it's kind of from the scratch. I suppose that people have some knowledge, and I want to check it in a very small
Just
quiz in
for
the beginning.
remembering a few things, I want to participate.
Yeah, sure.
You know the lights are not on the green screen, so it's not detecting the green color
I
perfectly.
can't change anything.
then this VA is way larger.
Detecting the green color.
It's like minus and
I believe that it's using this microphone from the camera.
so the plus or the number is minus on the A for the camera.
No, over here it says it's from the this headphone. Can you mute it? Just put this one like this.
Is it? Did anything change?
Wait, I'll
I'll just
audio input. Yeah.
move
I'll
this a
fix
little
it.
bit, and I will be able to. connect
Wait,
it.
I'll
Maybe
fix
more.
it. Yeah. So screen capture muted.
Yep. Do you hear me? Okay, fine. That's great. Okay, let's. Can we? How can we put this screen also? You need to. We need to duplicate it, right?
It's an extension you have that, right? You need to duplicate the
Yeah.
The moment you duplicate this, try to put it.
Okay.
Do one thing. Take the screen to that screen and we will start recording that on the screen.
Okay. No, it did work previously in this setting.
Can you take this one to that?
No. Yeah, I can. Maybe, but then we don't have here anything. Can we switch here to this? No, where is it? I don't see it. Okay, can you switch it to there? Yeah, oh no, this one. Yeah. Okay, let me make it full screen. There. Yeah, it's a bit complicated. Yep. Okay, nice. But okay, and I probably. But how can I? No, But I don't have other windows on that screen. Yes, but I don't have other windows prepared. Other desktops. What I have here. Should I? Okay, maybe I also need to move it. But no, I cannot. How can I? Okay, sorry, it doesn't work well on both. I want to switch between them, like I do with different desktops here. Yes. Okay, but to switch. Hmm?
Where is your presentation?
This is a presentation.
Can you take it to that screen?
It is there, was there. No, I just need to duplicate this screen. It's impossible. I need three. I need this one, this, and
Yeah.
yeah.
So let's take this one on desktop. On this
Which one?
this presentation. Can you open the presentation for me?
Yeah, this is the presentation.
I'm not able to select it here.
No, somehow it doesn't. I need to duplicate this screen there. Why is it different? No, it Okay, so do we expect somebody to come back? No? Not really? Okay, so
I'll tell you one thing. There's one problem. You are wearing green, and that
yeah, I see. Yeah, I didn't think about that in the morning. Yeah, okay. Okay, I hear there is small delay. Okay, thank you, Suraj. So, good morning, everyone. Welcome here. Glad that several people came. So, today I will be giving a lecture instead of Aki. And Aki asked me to discuss with you the finite element analysis, but not so much the math behind it. I suppose you're a little bit familiar with it, but more about how it can be applied, what kind of analysis can be performed with it, how it is useful, and this kind of stuff. Maybe inspire you a little bit for your future work in that direction. Okay, so yeah, this is my name, my email. You can contact me whenever you have any questions related to finite element analysis. That's pretty much the direction in which I've been working most of my professional life. So if you have any question, if you want to discuss anything related to finite element analysis, welcome. But before before I continue with technical stuff, let's make a small quiz. I want to discuss several things, and it would be nice to have your input. Like, it will allow me to understand a little bit more about how I should deliver this lecture, what emphasis where should I put emphasis, and what I should skip. Okay, so if you connected, that applies to online participants as well. Please go to Mentimeter, enter this com, and there is this quiz that I've prepared. I see that we have already 5 participants there. That more or less matches with the number of people in the room. So I guess people online are not. Okay, now it goes increasing. Very nice. So yeah, you will have this number on the next slide as well. So don't worry, I will. So the first question. So it's anonymous. It's not related to any stuff like grades, so on. Anyway, I suppose this lecture is not that much in the grading framework, anyways. So yeah, I thought, what do you think about this finite element analysis at the moment? Do you think you are going to use it? Okay. Wow, it's growing. So this is very, very cool. That I actually didn't expect from like what I discussed with Aki. I didn't expect that the first answer would be there. Will take the most votes. That's really cool. And yeah, the rest of people kind of appreciate the method, but not going to use it as a main tool. Yeah. And nobody responded like it's not useful. And the last question is it's kind of for fun, but if some people did answer that, I would know that I need to talk a little bit more about what the method is. And okay, then let's go further. So now several questions, I think I have 6 of them, about the finite element method, how well you understand it. They are kind of easy, some of them are a little bit tricky, but yeah, that's just how you I hope the first one is very easy. Hope so, but let's see. If you give a wrong answer, so in these questions there are right and wrong answers, but I don't care. I will not judge you if you give wrong answers. It will just give me a hint that where I should pay attention in this lecture. Okay. Yeah, I will show the correct answer. Like, let some other people vote. Okay, I think pretty much everybody voted who was participating. And yep. Okay, now it is increasing. The number of photos. Yeah, it's an easy question, but it's a little bit tricky, yeah, because this first part is actually included in the finite element method. So it's not completely wrong, people who answered that it's a method for splitting a body into multiple segments. It's not completely wrong. I would not say that this is the essence of the method or its main meaning or whatever, but this part is included. For sure, when you do finite element analysis, you make this mesh, you divide your body into segments. Okay, but the main mathematical essence of the method is that it's a method for numerical solution for partial differential equations. Well, honestly, not so much partial differential equations, but more weak formulation is used in practice. But that's still, it can be applied to any problems. So from this correct answer, it's kind of obvious that you can apply it to multiple different physics. And this is what we are going to talk about in more details today. Okay, let's move on. Next question. So what is not the area for finite element analysis? We discussed that it can be used for different problems. Okay, sorry. Yeah, it was here 6, 4, 5, 2, 8, 3, 2, 1. Okay. Did you get it? Okay. Okay, but not every problem. And I put there this word typically because technically you can solve any of those types of problems, approach them with the finite element method. But for one of them, it's not really used in practice. I have never seen anybody using. Yeah, I know that it's possible, but there are reasons, mathematical reasons, why it's in practice almost never used for one of those. At least in engineering practice. Yeah, for scientific computing could be. Wow, this is a nice distribution. Good. Yeah. Okay, so some people are still. Yeah, this is a good thing, like for this lecture, because it kind of indicates that you are not so sure about where you can apply it, where people do apply it, because this is exactly what I'm going to talk about. So it's not bad thing that a lot of people did not put correct answer. Yeah, in practice, it's fluid dynamics. So this is this branch of engineering computational science called computational fluid dynamics, CFD. And from the first glance, it's very similar to finite element analysis because it also includes this process of creating a mesh, like splitting your body or the area that you are analyzing the domain in segments. But the mathematical method is different. It's usually, in most cases, it's solved with a finite volume method, which sounds similar, but completely different mathematics. So it's based on balanced equations. The reason for that is in the equations. Navier-Stokes equations, they include this nonlinear convention term with the first derivative. And you can use finite element analysis. Technically, mathematically, you can, but you get quite bad metrics. And you have stability problems. So you have a lot of unnecessary problems. Whereas there is another method which is finally suited for this type of equations. So yeah, so that's why it looks similar, and people often tell that it's like finite element analysis. It's so ubiquitous, finite element analysis, that people often think that everything that is done in engineering numerically with software is finite element analysis. It's actually not. A number of methods is used. In electromagnetics, and other methods are used as well. But finite element analysis is quite commonly used in those. So I understand why this one, high frequency electromagnetics took the most amount of votes, because it's maybe sounds quite far from mechanical engineering. It is quite far from mechanical engineering, but finite element analysis is used there as well. Whoa. Electrostatic problems, that's a bit surprising, because it's basically a Laplace or Poisson equation, and basically the same as a pure electrostatic as a heat conduction problem, steady state heat conduction problem. So yeah, it can be. Probably the reason it took many votes again is that it's a little bit unfamiliar for you, but that's exactly what I'm going to focus on today, to give you a perspective of some maybe not obvious for you applications of the finite element analysis. Well, with contact mechanics problems, it's understandable that it's quite difficult, and it's difficult with finite element analysis. It's terrible with analytical computations. Well, for a while, people were developing analytical tools to estimate contact stresses in different situations, and there is quite basic Hertz theory, which did advance further, but in practice, what I've seen in engineering practice is it's mostly approached with finite element method. There are quite suitable tools for that. I will talk about them later. Yeah. Okay. Plasticity, it's part of solid mechanics. No problems with finite element method. Okay, a little bit more mathematical question. So not about application, about how aware you are of the math behind the method. Do you know what are the shape functions? Which kind of one of the core features in the method. And I put here 4 answers. One of them is correct. And I tried to use there some words related to finite element analysis in not correct answers also to in attempt to confuse you a little bit, but let's see how it works. Okay. Yeah, maybe that one that did not take any, I did not put enough effort to make it convincing. Yeah, it's not the right one. I mean, the one that has 0 votes. So it's good. Yeah, maybe it's not, but yeah. So this is kind of good. Yeah, overwhelming with right result. Yep, this is. Yeah, there's the second option. Yeah, maybe it is a bit confusing because it is a property of elements. There are different type of elements used, hexahedral, tetrahedral, if in 3 dimensions, but also pyramids and this kind of thing. But it's not what shape functions are called. Yeah. This is also what a property of elements, but shape functions is essentially what we use to interpolate this math behind it. Okay, this is good that I did not trick many of you here. This is hopefully quite simple. By the way, sorry, when should we end this lecture? At what time? quarter to noon. Okay, yeah, so just I'll keep track on time. So we have a bit more than an hour. This is good. There's not much left in this quiz, and yeah, then I will be showing you different stuff and talking, but I encourage you to participate in the entire lecture, not only in this interactive part. Yeah, there is a little bit of redundancy in the statement, so that 2D has actually nothing to do with it. It would be the same, the answer would be the same for 1D or for 3D. Elastic, kind of, yeah, it's not only for elastic analysis, this is true, the answer that is correct, but also for many other, most cases, but you can imagine a situation when it is not true. So I'll show you the answer. So yes, it's symmetric and square. And this symmetry, yeah, this is something that can be broken in few cases, but not in purely elastic analysis. So for instance, if you make coupled analysis, you have different physics involved simultaneously. You have elastic equations and you have some electromagnetic equations, or just simply electromagnetic if you have both electric and magnetic part and some circuits. Yeah, it can become non-symmetric. And it's kind of a bad thing computationally, because a lot of methods from computational science that are used to solve those equations are based on the assumption that the matrix is symmetric. So it's in practice when you manage to build a system with non-symmetric matrix in commercial software, it is possible in multi-physics software. Usually you notice that you usually get some warning about that, and you notice that the performance drops significantly. So the same amount of degrees of freedom, but you need much more time to solve the equations. Yeah, that's how it works. Yeah, but basically not much wrong answers. And this is maybe a little bit tricky. This has to do with understanding of boundary conditions. There is such thing called natural boundary conditions, which mathematically comes from a variational statement, which is used in practice in most cases, weak statement of the problem. And it's kind of what happens on the boundary where you do not impose boundary conditions. It doesn't matter are you using commercial software or your own MATLAB-based code or Python or whatever, but what do you expect to happen on the boundary? So it's mechanical analysis, so you're talking about deformations and stresses, and you apply some loads to a body, you apply some constraints, but you leave some parts of the boundary without specifying any boundary conditions there. What will happen there? Okay, I'll give it maybe a minute, half a minute more. People are voting. 9, 10 votes, 10 participants. Okay, yeah, so that's it. No correct answers. Well, still answers come that are not correct even after I show the right. Obviously, people might not see it, and it may come with a delay. But okay, this was really confusing, maybe, and tricky. And the last part, intuitively, it seems right that if I don't impose any restrictions, then it can be anything. But it's actually not what's happening. And yeah, this maybe Yeah, no, still people are insisting that this is the correct answer. People are voting for it. Okay, why it is not a correct answer? Because, well, that to answer it rigorously, that requires me to dive deep into equations and show you how it works. I'm not gonna do that today, but just on my fingers I'll try to explain. So mathematically, if you have boundary value problem, it can be a elasticity equations or heat conduction equations, whatever. So boundary value problem described in equations in partial derivatives, right? It requires boundary conditions. It's obvious even from its name, boundary value problem, because there are derivatives. So we do not. It's not enough to find a function that fits equations with derivatives. Yeah, because there is no unique function. So it's not unique. It's kind of easy, and we have find multiple functions that satisfy equations in derivatives. To have, in order for this problem to have a unique solution, we need boundary conditions. Yeah, that's why it's called boundary value problem. And there must be a certain number of those boundary conditions. So basically, at every point of your boundary, you must specify something. If you are thinking about equations, if you don't specify anything at a part of your boundary, then inevitably you will not have a unique solution. You can find multiple solutions that will fit these partial boundary conditions and the equations. So mathematically, to solve partial differential equations in a unique way, you need boundary conditions everywhere. What number of boundary conditions depends on your equations, on your variables, how many variables you have. Are you talking about just temperature or 3 components of the displacement vector or something else? So the number will be different, but it must be something must be specified everywhere. And in practice, finite element method is implemented in a way that if you don't specify anything, then you kind of imply that natural boundary conditions will happen there. What are natural boundary conditions depends on your physics, and not only on physics, but also on equations. Because, for instance, in electromagnetics, you can approach this exactly the same physical problem in different formulations, both finite element, but natural boundary conditions will be opposite, like when you're using scalar magnetic potential or vector magnetic potential. I'll talk about that a little bit more today. Yeah, so there are so-called natural boundary conditions. Where they come from? They come from this variational statement. I will show it very briefly a little bit later. And the important for this question is that in case of deformation analysis, yeah, how does it say? It says stress analysis. Finite element software usually uses the term structural analysis, which does not mean that we are analyzing, I don't know, the structure of things, but we are analyzing mechanics at its very core, like this deformational process or stress. To make it more obvious, I put stress here. So in this type of analysis, like where you want to find out how something deforms, natural boundary condition is zero force applied. So because there is this force in your statement of the problem, and if you apply nothing, then it means that if you impose nothing, then it means that you apply zero force, which kind of is natural. Okay? So if we have free surface, then there is no force acting. But since there is no force, then stresses cannot be completely arbitrary, because stresses at the surface are connected with the applied force. So the right answer, there will be some normal, actually. Yeah, it depends on your coordinate system that you're using to describe this stress tensor, but some components will be zero, so that the resulting force vector at the surface is 0 because you apply 0 force. So pay attention to what happens when you don't specify boundary conditions explicitly. Okay, we can talk about that later, but I have one last question, I think, left. Yeah, this is the last one. So I tried to put a number of fun words related to finite element analysis here, like isoparametric, hexahedral. Yeah, what else? Linear, kind of obvious. Some of the words are here just to confuse you, to trick you into skipping the right answer. Let's see how I succeeded in that. Yeah, this takes time to think, but it's really a very practical question, because when you choose the type of element, you need to understand what consequences you will have because of that, and consequences are connected with how stresses or how displacements or whatever will be distributed, because we impose some interpolation. So finite element analysis is about splitting the body into segments. This is right part actually, but then the most important, within each segment we assume that variables change in a certain way. And in linear elements, what's mentioned here, we assume that something is changing linearly. And to make it perfectly clear, I added this word displacement-based finite element analysis, because frankly, there are other formulations. Like in 99.9999%, I don't know its exact number, of course, but like almost everywhere when people are performing mechanical analysis, calculating deformation stresses, they use in engineering, they use displacement-based analysis. In some very peculiar applications, especially in scientific things, yes, people use different formulations also. But usually it is displacement-based is usually what you are dealing with. So if you are choosing a linear element, it's usually called this way, linear element in help to your software. Well, that implies apparently linear interpolation of displacements because it's displacement. And I did trick you here. This is kind of not obvious and maybe a little bit frustrating. And maybe a little bit contradicts to your observations. But let me explain. Take a couple of minutes. Maybe it's important since nobody picked the right answer. So displacements are connected to strains. How are they connected? How we can find strains if we know displacements, the displacement field? No idea. But you did some finite element analysis. And you did attend some courses, I forgot how it's called in your curriculum, about this type of, yes, this kind of course. They are called differently in each university, I don't know why. Sometimes it's called mechanics of materials, sometimes it's called strength of materials, sometimes it is called mechanics 1 or something else. Like even when we were talking about beams and rods, this type of structure, you did talk about strains. Okay, yeah, maybe it needs more explanation. Okay, so for now I'll just say it. So strains are derivatives from displacements, partial derivatives. So even in a one-dimensional case, you have displacement field, it will be just a derivative of this displacement field, it will be stress. You will have just one component of stress. In three-dimensional problem, you have three components of the displacement vector, and your strain is composed of 6 components. It's a symmetric second-order tensor, and it has 6 independent components, and those are made of partial derivatives from displacement field components with respect to spatial coordinates. Sorry? Not yet. I was just going to say about. Yeah, actually, this is much better if I take one ear off. So strains, you find strains by calculating derivatives of displacements. So if your displacements are supposed to change linearly within an element, then strains will be constant within an element. So element-wise constant. But this doesn't ask about strains, it asks about stresses. But stresses are connected with strains. In the simplest case, it's a linear relationship. It's Hooke's law, or generalized Hooke's law for three-dimensional case. And yep, so if strains are linear, then stresses are also linear. It may be more complicated, the relationship between them, but basically they still inherit this linearity. Why I said that it's not maybe contradicts with what you see, because if you use a finite element software, commercial software for instance, and you pick linear elements, you calculate distribution of stresses, and then you plot it on your screen with a contour plot, and you see that it's somehow changing. But that's only because of visualization. Because so what the software does in case of linear elements, so there are 2 neighboring elements, for instance, and one of each has one value of the stress and another has another. So they are connected at some nodes, and at this node, so the software just takes averaged value between those 2 values and shows it. And then the next node, then it will be different value, and so you can see some as if it is changing. But mathematically, like inside your method, you assume that stresses are constant within each element. And that's kind of strong limitation. So if you're using linear elements, you must realize that it means that I am assuming that within each element, stresses are constant. You can make a fine enough mesh and it will cause no problems, of course. But if your mesh is quite coarse, like you have 2 elements across cross-section, which may sound okay, but if you understand that really it's constant stress within each other, you have only one step across your cross-section, for instance. It may give you a hint that you should either use finer mesh or use higher order elements. Quadratic elements are usually available. If we're using quadratic elements, then displacements are distributed according to second order polynomial, and then we have linear distribution of strains and stresses across an element-wise. Okay, so yep, that's it. So let me get back to my presentation. So we have some time left, a bit less than an hour. I hope it was fun to remember things. So we more or less covered the first, at least partially, first takeaway that I would like you to have from these lectures, to some refreshment of your basic understanding of the finite element method. But I will talk about that a little bit more. So then what else? Maybe the main part of today's lecture is that for you to make you aware about what type of analysis are made in practice done with finite element method, and also what software is used mostly in industry. Like there are hundreds of different software, but I will just talk about maybe the most popular ones. Okay, so since there were quite a few wrong answers about basic understanding of finite element method, I will go through these slides, well, not super fast. Fast, but not super fast. So there are several ideas behind the finite element method. And the first one, I think you covered them. Most of you who replied to the first question, the first answer, which is not entirely correct, but I agree that it's partially correct because this is what happens. So we do discretize the domain, our computational domain. It's not necessarily a body. So I don't like to say our body because it may be not a body, it may be a vacuum outside our body if we are calculating electromagnetic fields, for instance. Maybe even electromagnetic waves, how they are propagating. So there is no body, but there is some space or domain. Okay, and between them they are connected via nodes. So this is quite easy. So naturally, according to the nature of your dimensions of your problem, so if it's two-dimensional, you can think of different shape of elements. What is used in practice? Well, this is what is used in practice. All of them that I show here, they are used. So triangular or quadrilateral elements, linear or quadratic. There is one important thing that I want you to maybe to take away from this lecture if you don't recognize that yet, is that finite elements do two things simultaneously. They are completely different mathematically, but they are done in the same way in most cases. So the first thing is the discretization of your domain. So this shape of the element, it's part of its nature, how it discretizes. We assume that the domain consists of this linear part. So the boundary will be with linear segments in our approximation. Or it can be quadratic, so this can be boundary of our volume. Obviously, if we are analyzing this type of structure, then quadratic elements will give much better geometrical approximation of this body or this region that we are analyzing. This is one thing. And another thing is that we assume some interpolation of the unknown function, displacements or temperature or something else. I will go to that later. So for now, okay, this is a little bit more in depth. So if we are talking about three-dimensional, then there are basically a little bit more shapes. And what you may be dealing with a lot is tetrahedral and hexahedral mesh. But if you try to connect, okay, so in practice, why I want to talk about that a little bit. So in practice, this first step, discretizing your domain, is quite a big work. Like if you have a complicated structure, I don't know, gas turbine or whatever with blades or something, or a vehicle, a car. I will show you some examples later. So if you want to discretize it into finite elements, it's not an easy task in general, because you need to take care of this connection, because all your elements must be connected at some nodes. They must be sharing nodes. So I don't know if you have much experience in that, but it's for complicated structure, this just meshing part, how it's called in engineering, it really can take days, it can take weeks. Well, in some cases maybe it can take months, but it's not typically. So usually it's people try to simplify the work, so it at least it doesn't take years. Well, it doesn't. But you can surely spend days and weeks on just this discretizing of the domain. And if you you will be using some tools, so automatic tools, so measures, so tools for creating this mesh. It cannot be done completely automatically for arbitrary because of many things, because from CAD system it usually comes with some gaps, some overlaps, so it's not so precise, but you need to be precise in finite element analysis because you need to ensure this connection between elements, otherwise they won't work together. Nothing will work well. So, and more for three-dimensional, what can you done more or less automatically is do the mesh with tetrahedral, provided you have good body, I mean good model of a body, so without any gaps, without overlapping parts, without any duplicate areas, this kind of stuff. No matter how complicated is the shape, you can automatically generate a finite element mesh with tetrahedral elements. It's usually not the best thing to do because of resources. So for the same size of the element edge with tetrahedral elements, you are going to have more elements than you would have with the same edge of hexahedral elements. This is one reason. Another reason is the numerical accuracy, that in general hexahedral elements provide better accuracy than tetrahedral elements. So people try to do it with hexahedral elements, but it's sometimes not possible, just automatically at least. So it's a complex shape, and the program doesn't know how to split it into hexahedral regions. So what people do, they split the body in parts, they mesh one part of like a rectangular part, like a cube, with hexahedral elements, and the remaining part, I don't know, an ear of a bunny or whatever is left in your structure, with automatically with tetrahedral. But then you need to connect them, those two parts. They still must have shared nodes. And if you try to connect this kind of element with this kind of element, you are going to have some problems. They don't have matching faces. I told you, you can match some nodes, but the faces don't match. And to connect them accurately in a proper way, people use these pyramid elements. So this is what you can use to connect hexahedral part of your mesh with tetrahedral part of your mesh. And yeah, also prismatic elements can help, of course. That's why we actually need all of them. So this is what about finite elements. Then the second part. So this was about, the previous part was about geometrical aspect, like splitting body into elements, different type of elements. But another super important part is interpolation, what is inside your element. How do those elements, how does this splitting of your body help you to actually solve differential equations? And this is done by this second part. So we impose some interpolation of the unknown function within the element. If it's linear element, then it's linear interpolation. If it's quadratic element, then it's quadratic interpolation. A known function in displacement analysis is displacement vector, 3 components. Okay, and this geometrical representation, what we talked about, that selection of certain type of element imposes some geometrical assumptions. And this lies actually here. So when we will be using for calculating what's happening inside the element, B-normalized local coordinates, but then you need to connect them with global coordinates, x, y, and psi eta here. And the connection is that with Jacobian matrix, and this includes derivatives, partial derivatives, and this is where this geometrical part lies. So what is this interpolation of the unknown variable? So let's take the simplest example, the thermal analysis. Simplest because we have only 1 degree of freedom. It's temperature, it's scalar thing, scalar value. So this is how the simplest linear interpolation of a scalar quantity, in this case temperature, within an element looks like. So we have psi and eta local coordinates within an element changing from -1 to 1. And we have some values of the temperature, assumed value at the nodes. We have 4 nodes. And this is linear interpolation within it. So it looks maybe a little bit long, but it's really the easiest case for two-dimensional analysis. You can make it easier only going to 1 dimension. When you go to 3 dimension and when you go to quadratic, it becomes much more complicated. Okay, anyways, and so these things, they are called shape functions. One of the questions was about shape functions. So they are doing this interpolation of unknown values, unknown variable. In many cases, it's displacements. But the same shape functions, in most cases, used to describe the shape of the element. So if we assume that it's linear, so those are lines, so we interpolate shape of our body with these linear elements, we can use basically the same shape functions to describe connectivity between those coordinates, and they are kind of included here, derivatives of those functions. Okay, and this strange word that I used in the last question, isoparametric element. And some people didn't like it, obviously, and they put their vote for an element cannot be isoparametric and something else. Well, it can, actually, and in most cases it is. And in commercial software, that's pretty much everything that you have. Pretty much all elements that are available there are isoparametric. Isoparametric means that we are using the same order of approximation, the same shape functions, basically, to interpolate geometry and to interpolate unknown value, unknown function. This is what is inside our equations that we are trying to solve. Okay, so I don't want to spend more time on that. So just to one statement regarding to this question about boundary conditions. So the equations are, for practical reasons, again, it's quite a long story to talk into detail about the reasons, but just you can take it for granted that for practical reasons, in most cases, finite element method is implemented based on variational statement or weak statement, weak form of equations. So this is an example of variational formulation for heat conduction problem, two-dimensional. So we have a functional. So it's some rule that takes in a function, distribution of temperature, field of temperature, and gives out a scalar value. And the nature is to find the task, the mathematical problem is to find this function distribution that provides this functional with a stationary value, or in most cases, minimal value. It's a bit easier to speak about minimal values. It's not necessarily the case. There are other variational principles, but this actually is a minimum value in this heat conduction problem. Okay, with some restriction. And why I put it here is because there is this applied heat flux on the boundary in heat conduction problem. It is included in this variational. And if we don't imposing it on the boundary, like ourselves when we are setting up the problem, then it just takes 0 value here. So if you don't put anything on a boundary, then you get 0 applied flux here, and that gives you that something will happen on the boundary according to the 0 heat flux on it. Okay, then we do this finite element. We apply that interpolation within finite elements, and we calculate value of these functional using that interpolation. I will not go into details here. We don't have time for that. And then we apply this variational principle basically to this equation. So we apply variation to this temperature, T, the vector, the column of unknown values at nodes. And what we end up is this system of linear algebraic equations. And we solve it and we get the global vector of temperatures. Those are temperatures at all our nodes. Okay, that's basically how it works in very, very short details, skipping a lot of things because we don't have time. Okay, do you think we can discuss applications now? Or is good? So I tried to make some kind of classification of problems that people are solving. Of course, you can, since it's general method for solving problems that can be formulated in differential equations or in variational statement. Of course, you can apply it to almost everything that you can describe with those things. But what people do in engineering, in mechanical engineering, is the first heat conduction problems. First, because it's like the simplest mathematically, because we have only 1 degree of freedom temperature, and it's a scalar quantity. No vectors, no tensors. Well, there are vectors in the analysis. There is heat flux vector, there is temperature gradient vector, but it's kind of more easy than mechanical, this deformational situation when we have 3-dimensional displacements, we have second order tensors for stresses and strains. Okay, geometrically quite clear, except for 2D. So what does it mean, a 2D problem in thermal analysis? So it's either plane, so nothing changes in the direction across that plane, or it's axisymmetric. Yeah, it's a little bit different mathematically. It all looks the same on screen of your computer, of course, but you apply different assumptions. So if you run thermal analysis in 2 dimensions, you have a choice to say that it's to let your program know whether you want it to be a plane thing or you want to be axisymmetric. So you are considering a cross section of a body of rotation, for instance. Okay, so if nothing changes in time, so it's called steady state in thermal analysis, like some equilibrium state. We apply some heat flux, for instance, and the heat goes out through different ways, and there is some steady state. So this is steady state analysis and obviously transient analysis. It's kind of more or less obvious, can be linear and non-linear. Of course, non-linearity comes usually from the dependence of material properties like conductivity or specific heat on the temperature. So you don't know the temperature at the start of your analysis, but while you are calculating it, you are updating the properties, and then it becomes nonlinear. Another source of nonlinearity comes from boundary conditions. If you have boundary conditions, do I have something? Yep. Okay, let me show this, some pictures again. If you have some radiational heat exchange boundary condition according to Stefan Boltzmann law, for instance, it's also nonlinear. It includes 4th power of temperature. Heat flux depends on 4th power of temperature, obviously nonlinear. So what can you use it for different circuit plates, like everything you have in your PC or in your mobile phone. They all include various elements, usually semiconducting elements, transistors and so on, which generate heat, and processors which generate heat, and yeah, it can make a difference. You can use thermal analysis to find out the distribution, to determine whether you need some additional radiator or not. sounds quite approachable and down to earth. Can it be more exciting? Yeah, I'd argue that it can, because in this type of problems, it's never the last resort to your computations. You can always make experimental test. Okay, so we don't care very much. We'll just produce this plate, and then we will test it. And if it doesn't hit too much, then it's okay. So we can just make it and test and measure temperatures. Quite straightforward. But it's not always that the case that you can do that. And I wanted to show you one example of a problem where it's completely impossible, and when you deal with absolutely crazy temperatures. So this is a ITER, one of the recent pictures they posted on their website. On the left one, it's a model, but it's thermonuclear experimental reactor that is currently under construction in France. And it's an international effort, and many say that it's like the most engineering standpoint, it's the most challenging thing that humanity has ever created. There are several systems that are far beyond, that set parameters far beyond previous records. There's a vacuum system, this is a plasma heating system, and this is a superconducting magnetic field system. So people have never done anything with this amount, this volume of vacuum, of such strong vacuum ever, never even close. People have never produced so many superconductors at all. And this plasma heating is also very, very innovative thing. So it is for controlled thermonuclear fusion, experimental thing to show that it is possible to have a sustainable thermonuclear reaction that produces a lot of energy, a lot of heat. That if it works, then the next step will be to utilize that energy. This is not the ITER's purpose. This is the purpose of the next stage, the demo reactor and some national. And this is one of the calculations for demo that I wanted to show you. Okay, but what's the problem with thermal analysis? Well, the problem is that you have this quite hot plasma. How hot do you think it is? Like in degrees, Celsius degrees? No, much more. No. 1,000 times more. It's about 150 million degrees. Crazy, right? And at this point, it doesn't make any sense to specify which degrees, like Celsius or Kelvin. The difference in 200. Who cares if it's 100 million? Actually, about 150. Yeah, it's much hotter than actually the sun. So the estimated temperature at the core of the sun is about 100 times less. But the sun has basically, it's kind of close idea. So we want to use this thermonuclear synthesis or fusion reaction that generates a lot of heat. This is what happens on stars. Hydrogen atoms collide and combine into helium. It is very simplified. It's not accurate description, but just to give you some idea what's happening. But the reason why we cannot do it the same way as it's done on the sun is because we don't have that much space. Sun is much bigger than the Earth, and it can afford to have something that happens at very low probability, because it's very large and it happens very low, but still it's enough of those happenings, those like fusion reactions, collisions, that it produces a lot of heat and reaction is sustainable. In a smaller scale, we are much smaller scale, we have to raise the temperature. That's the reason. Well, basically, there is a little bit of problem how to keep this a little bit hot body, much hotter than the sun. And it's kind of solved in these tokamak type systems. It's solved by keeping it with magnetic field. Because obviously you cannot make any vessel that will sustain a body of that temperature. So it's kept in a vacuum in magnetic field. So it's like hanging in the air, except for there is no air, there is vacuum inside this whole thing. Yeah, this obviously shows you how the plasma might look like. Obviously, you will not see this kind of picture with your own eyes, but it depends on the spectrum and range. But some infra. So the diameter characteristic dimensions here will be something like 7 meters inside. It's calculated for that. So there is this plasma thing that is kept with magnetic field. It turns out to be not very stable. It wants to go away. So the margin of this stability is not so high. And we know that from previous this type of reactors. It's not the first experimental reactors. People have been doing them for more than 50 years already. But this is the largest one, by far larger than all previous ones. And so we know approximately how it happens. So this it can happen because of an earthquake, for instance. Because of earthquake, this plasma moves and it goes beyond the stability region, and it then hits the wall of this camera. So yeah, the characteristic dimension like 7 meters is within this space where the plasma is. This whole cryostat building is a bit larger. Yeah, so these kind of things have to be calculated. And this is one of the reasons people have to rely on the importance of finite element analysis. In this kind of things, people have to completely rely on finite element analysis. Like in some things, we cannot test. Like we want to know what temperature will be in these segments that are facing plasma. So there is a distance they are not touching. There is a vacuum, distance of vacuum, but it's radiating heat still. Luckily, it does not radiate according to Stefan Boltzmann's law. Like if it would be the heat flux proportional to the 4th degree of temperature, nothing would survive. But it radiates with that high temperature. It radiates in ultraviolet and even shorter waves rather than infrared waves. So, and the math is a bit different. Luckily, it doesn't radiate that much as we would expect it from our everyday things. But still, it radiates a lot. And we want to know how hot will be, how we can design this cooling system. Yeah, obviously, everything needs to be cooled there with kind of water. But how we can design it? Can we test it? Do you have a 100 million degree heated up body? I need to test this divertor. This bottom part is called divertor element, and how well it is cooled. What will be the temperature? No way. Well, we can a little bit approach using other experimental facilities that already exist, like there is a JET, Joint European Torus, in England. It's the closest thing that we have to ITER in Europe. It's much smaller, like something like 1 meter instead of 7 meters. But it's we can test some things, and of course some tests have been done. But 150 degrees, no way, we don't have it there. So we have to rely on analysis, calculations, and mostly are done by finite element analysis. This is one example of calculation. This is tungsten elements. So tungsten is quite tough. I mean, with respect to melting point, sorry. melting point. So this calculation from this paper shows temperatures up to 1,600 degrees. So if it were steel parts, they would probably melt already. Tungsten can survive that, but still this is quite hot for it. So for working of this part, it was considered too hot in this paper, and they want some redesign already. Okay, this is kind of extreme example of thermal analysis that you might encounter in engineering life. So let's go to mechanical analysis. Probably what most of you have the most experience and will be facing the most in your professional life, because of the first slide, remember, everybody told that they are going to use finite element analysis. And I suspect that in most cases it will be this so-called structural finite element analysis. It's not very accurate word, but finite element community kind of adopted it in this sense of mechanical deformation movement analysis, structural. Okay, there is a little bit of more classification. First of all, 2 dimensions. It's a bit more tricky here. Like you can simplify your problem to 2 dimensions in different ways. I was thinking to add one question about that in the quiz, but decided that it's enough for now. So the most those are plane stress and plane strain assumptions or formulations. Like you assume that something is plane, and literally, and this, if you forget what it means, you can think about this name. It's very accurate. Plane strains assumes that certain components of the stress tensor are 0. So the stress tensor is kind of plane. So 1 normal component and 2 shear components, everything that includes the naming of your third axis, that is 0. So it's kind of plane. And the plane strain assumes the same about the strain tensor. And they are quite different mechanically. And another is sometimes called 2.5D. It's axisymmetric because on your screen it's still plane, like you have rectangular and so on. But mathematically you have this third degree also, like in your tensors, in your stress and strain tensors. They are not, neither of them is plane, and nor is the displacement vector. So kind of yeah, well, the displacement vector doesn't have this circumferential component, of course, but yeah, so it's sometimes called 2.5D. 3-dimensional solid elements, like you just approach your domain and you discretize it. But there are also beams and shells, which you have some experience dealing with from at least your finite element course, I suppose, on the bachelor program. And those are simplifications that allow us to solve certain types of problems at easier, at less computational price. Like if they are thin, like shells, or if they are long and small in 2 other dimensions, like beams, then we can apply some mathematical assumptions and simplify the equations themselves, and then apply finite element method. There is some specifics about them. I'm not going to go into that today. So statics, dynamics is quite clear. One additional type of analysis that I wanted to mention here is a little bit not obvious. Sometimes people forget about it. It's different mathematically. It's eigenvalue analysis mathematically, and it is used mostly for 2 things: for model analysis or for stability analysis. And I think I put here some about stability. So like this. Euler stability of a beam, of a column. This is quite clear. You probably know that after a certain amount of force, then we don't have anymore a single equilibrium point. We have several of them, and like that. But in practice, this is one report of European Commission from some years ago about the buckling damage on this kind of structure. This is also buckling, so the load exceeded the stability limit, and terrible things can happen. So mathematically, it's a bit different. So mathematically, it's eigenvalue analysis. If you know that, then I don't probably need to add anything. Some words about nonlinearity. What has it to do with everything? Though there are quite many sources of nonlinearity in this type of problems. Most of, like, I would categorize them in three categories. Geometrical linearity. This is when we are talking about large displacements, large rotations. This is very much connected with multi-body applications, obviously. And you can think of it as when the movement of the body affects somehow its properties in any way. Material nonlinearity, if we have hyperelasticity or viscoelasticity, plasticity, anything like that, something that material doesn't behave linearly. And there might be contact interaction with other bodies, which has also something to do with multi-body applications, but not only. And more generally, there might be other types of loads that depend on the deformed shape. So as the body deforms, the load changes also. So contact interaction kind of falls into that category, but is also quite special. So this is done with finite element analysis. I remember that a lot of people put these contact problems into something that is not done with finite element analysis typically. Well, while I agree that other methods are also used, it's not uncommon to use finite element analysis for it. Okay, I picked just one example of structural analysis that I wanted to discuss with you. It's quite representative. It's quite complicated. It includes all types of linearities that I mentioned on the previous slide. And it also includes shell statement. So it's crash test simulations. You know that cars nowadays are very much ranked according to their passive safety, what kind of passive safety they provide. And how do people achieve those good rankings, like 5 stars? Well, they achieve that by running a lot of simulations, like really a lot. I heard some years ago, maybe it's a bit outdated, I don't know, but what I heard that for one physical crash test, like big companies, car manufacturers, they do about 400 of virtual crash tests. So the same thing, but with some modifications in the car, but performed digitally. And I'd like you to watch this YouTube video. I'll try to show on it. It's from the software manufacturer. Yep, it's here. So this is a Beta, there's a Greek company providing some software that is widely used in crash simulations in car manufacturing. Okay, maybe I'll put a pause for 1 second. I'll do that several times. Sorry, you can watch it again without my comments if you like later. So this is a real test. This is not simulation. And you can see that a lot of wires are there. Well, obviously the people want to wires, cameras, and this kind of stuff. And if you think, and because intuitively you might think that doing physical crash tests is so expensive because you need to break, you total a car. But actually this price of the car is just a fraction of cost of the crash test. Everything else costs much more, which some of those things can be used again in other crash tests, some of them not. But actually the cost of the crash test, physical crash test, is multiple times more than just the cost of the single car. A lot of businesses involved there, of course. Those one companies are providing those dummies, and to get a certification, you can only use a dummy from this company and this kind of things. And You need a lot of, like, something about at least 100, maybe even 200, I'm not sure, but not less than 100 of sensors are placed across the body of the car, not only of the dummy, but the car, and they are measuring acceleration at different points. They are measuring how the body deforms during the crash. So it's quite complicated stuff. Yes, this is real crash test. Yeah, but now on the right we have, I'll pause a little bit again, we have simulation. This is finite element analysis. So it doesn't show the finite element mesh because this doesn't matter, but the similarity, I don't know, from my perspective, it's overwhelming. So how the hood deforms, how everything, well, there are a lot of this kind of videos you can find on internet. Maybe some will impress you even more, but and it's super difficult. You see that there is plasticity, there is some damage, there are welding spots that are being destroyed, disattached, and there is high rate plasticity. So I know that people use a lot of different curves for plasticity for different deformation rates. And to get this kind of similarity visually, you need to be very, very accurate. You need to take into account a lot of plastic parts. You need to take into account glued parts that they can split under certain loads. You need to take wheels, a lot of things that you need to have inertia carefully, all contact interactions. Like it's crazy how accurate your calculation should be. And on the slide previously, I showed there is one plot. So it's typically what people measure in real tests in crash test simulations is the dependence of acceleration, how it changes over time at different points. Accelerometers are placed there. And these simulations, well, when they are done well, of course, they match those experimental curves within 5% margin, like all along during all the crash tests at all 100 or more points where acceleration are measured. So I don't know, it's from my point of view, it's super impressive. Well, there is this, the airbag is deployed and is deployed in finite element analysis. And obviously what accelerations you will have on your dummy, like there are a lot of accelerometers placed, and you can measure those accelerations in finite element analysis, and you should match those experimental things. And it's affected how this airbag is deployed. And it's another interesting thing, right? How to simulate that correctly. Well, people have learned how to do this kind of simulations. Well, maybe once more I will pause a little bit later. Yes, so again, striking similarity. Well, maybe here. Yeah, and another view from the bottom, like how many things are accounting for in the model. How crazy. Of course, it's not a single person that makes this entire model. If you have some experience in preparing finite element mesh of some parts, you know that it takes time, but it would take like a lot. Of course, many people are doing the car model is split into parts, and one person is preparing mesh for one breakend and another for another axle and so on. And then it's all combined according to certain rules. So it's a collaborative effort of a number of people. It's only just one method or sort of. Yep. Well, I don't have exact numbers, but what I heard that they are using supercomputers because these dynamic simulations with explicit time integration, finite elements and explicit time integration, they are quite well parallelized. And so it depends, of course. Of course, big car manufacturers, they're using super powerful supercomputers. But I don't think that it takes weeks. I think that one like this entire simulation, it's a matter of a day. Yeah, I think just yeah, of course. Yeah, people are using a lot of them in parallel. And actually, what yeah, and they are not only running them for existing cars. They are running for cars that are designing, and many of those cars will never see the light because companies are designing much more cars than they are then producing. Yeah, it's maybe expensive, but the market changes, and by the time you have designed it, you might see that there is no market value in this type, and we need to design something else. And yeah, so yeah, I don't think it's hours, but several hours, but I think something magnitude of 1 day, typically simulation. Maybe a bit faster. I'm not sure. Okay, so I'll switch back to my presentation, and yeah, and we are running out of time. Do you think we can make it longer, 5-10 minutes, or we should finish in time? Okay. Okay, if you need to leave now, no worry, I understand. I want to skim very briefly through electromagnetic simulations because this is something that almost nobody thought. Well, many people thought that this is not what is done with finite element analysis, and it's understandable because I cannot just put it in linear, nonlinear, this type of things, just for electromagnetic analysis, because there are quite many, at least 4 large branches. And I need to distinguish between them before I say anything else, before I can say anything about degrees of freedom, about time integration, and so on. They're quite different. And the reason for that, well, I put a bit of equations here. I won't dive very deep into it. So those are Maxwell's equations. You are probably more or less aware of them. So they include, each of them includes 2 vectors for magnetic field and 2 vectors, not each of them, but they include 2 vectors for magnetic field and 2 vectors for electric field. Those 2 vectors within each field, they are connected through constitutive equations. Something like similar to Hooke's law in mechanics, but it can be that simple as well, but it can be more complicated for like permanent magnets and other things. And yeah, there is also current with it connected to electric field. But the problem is that practically nobody solved them in this form, like for any type of problem. It's kind of frustrating maybe, but we really need to simplify them to be able to solve and to get practical results. And there are 2 or at least 4 categories of simplifications are here. So electrostatic and magnetic static, they share the same simplification that all time derivatives are 0, and then each of them assumes that the opposite field is non-existing, only electric or only magnetic. Low frequency electromagnetic analysis gets rid of just this one term, which is called displacement current, and it makes a lot of difference computationally. Like the equations change significantly, even though it can be not obvious from this form, but it does change things. And for one practical consequence of that is that if we do neglect those displacement currents, then we don't have electromagnetic waves. So imagine like solving those equations in whole, like without simplification, would imply that for any solution for any electromagnetic problem, I don't know how the current is flowing or what is the magnetic field around this permanent magnet or this current wire, you would need to account for everything, for all electromagnetic waves that are emitted from all the parts, and you would need crazy space resolution and so on, and it's really not feasible. So this simplification is done quite often. It's quasi-static, quasi-stationary simplification, so-called. It still keeps this dynamics. This first derivative is still kept. So for instance, magnetic induction is something that we can still account for, but what we don't have electromagnetic waves. When we want to deal with electromagnetic waves, it usually falls into this high-frequency electromagnetic category. And most cases, time harmonic assumption is made. So we are assuming that quantities are changing according to sine or cosine, this type of things. And of course, that simplifies a lot. Okay, that may be a bit boring, but after I needed that to explain why I need this distinction. And dimensions, oh, sorry, this came from previous slide. Plane stress has nothing. Plane stress have nothing to do with electromagnetics, of course. But some not obvious thing is that there are some kind of shell elements, and it's quite a recent development. So this is the article when it was introduced in 2012. Shell elements for certain types of electromagnetic analysis. So they kind of exist. Mostly all computations are done with solid elements. With degrees of freedom, there is quite a variety of what you could have there. Usually problems are solved with in terms of potentials. So they can be scalar potentials and they can be vector potentials. And they can be also time-integrated potentials. And if you want both fields, electric and magnetic, combined, then you will have to have some combination of degrees of freedom belonging to both physics, both fields, electric and magnetic. So this quite is not so rare that you're going to have 4 degrees of freedom at each of your nodes in this kind of low-frequency electromagnetic simulation, for instance. And there is one peculiar thing that I just want to mention, edge formulation. So those degrees of freedom, as you know, they are associated with nodes. But actually, that's not the only way you can do that. You can associate degrees of freedom with edges of elements. So these kind of things are associated not with 2 nodes, but with the edge which goes between those nodes. You still have 4 edges for rectangular elements, so you have 4 degrees of freedom, 4 sets of degrees of freedom, but they are associated with edges, and this direction, this space orientation of the edge can be used then in simulations, in calculations. So it's a little bit peculiar thing, but just for you to be aware of. And I'm very close to closing this down. So some examples. So with high-frequency electromagnetic analysis, what you typically types of problems that are solved, like you have an antenna, like transmitting antenna, what kind of waves it transmits, how should you design your antenna, this kind of thing. Also electromagnetic compatibility because between parts, like what interference one electromagnetic equipment causes on another, this kind of thing. Low frequency electromagnetic, this is a nice example, wireless charging. So Faraday's induction law, so current flowing in one coil induces time-varying current, generates a time-varying magnetic field, which propagates through space and induces currents in another current. This is how electromagnetic induction works, and wireless charging is a good example of this type of low frequency electromagnetic analysis involving both electric and magnetic fields. Magnetic statics often deals with permanent magnets. This is an example from COMSOL, one software about how iron rod is attracted to a permanent magnet, how to calculate force, this kind of stuff. Electrostatic may be a bit boring. I put here example from my own paper to make a bridge to coupled field analysis. Like this is also a kind of beam type structure. So we used little bit non-standard techniques. Here that is bending. So we apply some electrical charge, some voltage to this beam, and it's then the bottom part is grounded, so it starts bending, and how we can calculate how it bends and what numerical tools, methods we can use for that. So, but of course, this goes much further than this coupling of different fields and different kind of multi-physics combination. Pretty much everything can be combined with thermal and with structural analysis, and you can even run simulation that simultaneously includes thermal processes, mechanical processes, and electromagnetic processes. But you need to think strong whether you really need that, because when you combine those physics, it gets much more difficult computationally. So my last slide was, I can talk about this a lot, but I don't have time. So if you later have questions, you can ask. Just wanted to mention you some of the most famous used finite element software that is used in industry. So historically, the big three have been ANSYS, Abaqus, and Nastran. Nastran was picked up by several. It was initially a NASA development. It was picked up by several companies. So there are different sim center. This is by Siemens nowadays, Nastran. MSC by MSC company. Well, ANSYS is super common in different type of engineering. A lot of companies are using it. It's a standard in certain industries, like in nuclear engineering, for instance, this ITER project that I mentioned, that one of standard software that is used for simulation there is ANSYS. There are codes for so-called explicit dynamics, meaning that explicit time integration scheme is used in connection with finite elements. And what ANSYS, it includes now this LS-DYNA program. This is something that is super commonly used for crash test simulation, what this kind of thing that you saw. Another software that is often used is Abaqus Explicit. So there are two branches. The Abaqus is a little bit more, has been a little bit more for, more well suited for introducing your own things, like own elements, own material models, constitutive models, but that can be done in ANSYS as well. Abaqus takes in Python scripts, which is quite convenient. Nowadays, super popular. ANSYS uses its own language, APDL, ANSYS Parametric Design Language, which is a little bit Fortran similar historically. Historically, all the finite element codes were first developed in Fortran. This was the first language that introduced powerful metrics computations. So nowadays, many of them have been rewritten in more modern languages, of course. COMSOL multiphysics is something that is also very useful for those who want to, especially for those who want to develop own things, introduce your own equations, something that is not typically possible with other commercial software. Like it's more equation-based, more mathematical, about a little bit less focused on industrial applications. It was initially developed by a Nordic MATLAB distributor, and then it became a separate company, a Swedish company. And Altair HyperWorks has been gaining population lately. Yeah, so those are the main that you will probably encounter some of them if you if you really will be using finite element analysis in your professional work. Of course, there are hundreds of others, and you can write your own codes. There are hundreds of open source codes written for finite element analysis in MATLAB, in Julia, in Python. A lot of things are available, but this is what is like the major things in industry. Because in industry, often you cannot use any tool. You need to use certified tool to take your results accepted, and that is not always possible with own tools. Okay, that's it. So I think I will stop now streaming.